It's my pleasure to introduce you to afternoon semi-plenary talk. Carsten Trunk will speak on perturbations of periodic Sturm-Liouville operators. Please.
Yeah, thank you for introducing. Yeah, you mentioned the title. So it is a joint work with Jussi Berndt and Philipp Schmid. He is a PhD student of mine, and Gerald Teschel from Vienna. Okay, and well, the topic is perturbations of periodic Sturm-Liouville operators, and I will spend, let's say, half of the time a little bit for the background. Let's say I will not give a really detailed background, but you will see. So, what is the object of the talk? Well, it is let's say a standard Sturm-Liouville equation on the real line, but the main focus is here that the coefficients are periodic and locally L1, which you always assume, let's say L1, but they are periodic, and this implies many nice properties. So very short history. Everything started with a quite, I would say, famous paper of Hill with this long title. There he described something about, let's say, stability of lunar motion, let's say. No? And for this he used this equation. This is here my second topic. So this was the starting point, and then came Floquet, or it was more or less at the same time like Hill for the theory of solutions, and then pops up quantum mechanics and so on and so on. And you know this is a somehow one-dimensional Schrödinger. We can view it as one-dimensional Schrödinger equation, and it gives a lot of applications. I don't discuss these two applications here. Well, one could, but this is not. I just mentioned it. This is stolen actually from Wikipedia, so it's not it's not really well researched. But what I also found is it's not called ponytail conjecture. This is just for the purpose of this talk, but it is something on the ponytail, and this gave the not the real Nobel Prize. Be careful, it is the ignorable Nobel Prize, I think it is meant with this. Yeah? In 2012, in physics, they have several Nobel Prizes, so it became somehow famous because of this Nobel Prize, pseudo Nobel Prize. I will tell you a little bit later on. I found this funny somehow. Okay, more applications. This is the one I mentioned in my abstract. Yeah, you can model atomic nuclei in crystals. No? Okay. And let me shortly discuss a little bit our topic for today. Our topic is not, I will start in discussing the unperturbed operator and properties of the unperturbed operator, of course you have to do. And then we want to perturb it. Yeah? And here is my very short, very short mathematical background. Who has done what, and well, so our unperturbed operator is the one with the zeros in the coefficients, with the indices zeros in the coefficients, and the perturbed one will be and the perturbed one will have ones. And well, what is known? Well, if the weight, so the first one is the weight, then we have in front the first derivative of f, we have this p0, and q0 is some kind of potential. Yeah? And there's a lot of research if r0 and p0 are 1. Yeah? And there's some some results are known for the perturbed operator if the weight is the same. Yeah? If you don't change the weight. The weight is a little bit crucial. If you remember in Sturm-Liouville theory, you put the weight into the inner product, right? And if you change the weight a lot, you also change the topology of the underlying space, and this becomes very, very, very difficult. Okay, some names. Let me drop some. You know, in Sturm-Liouville, there are so many players in the game that you can give easily very long talks just on the development of the history of some problem. Yeah? So let me do it very short. The main thing is the following. Again, what I said, we couldn't find any paper which addresses the changes of the weight, and most papers also don't touch the coefficient in front of the first derivatives, the P0. Yeah? There are some papers. So let me mention Fritz Gestesi, Rofe-Beketov, Carl-Michael Schmid, Barry Simon, Gerald Teschel, Joachim Weidmann, and maybe the best citation, maybe the best, I didn't put it here, maybe the best citation is the book of Braun, Eastham, and Carl-Michael Schmid. I mentioned him. Also, there are some papers of Carl-Michael Schmid, which I don't discuss here in detail. And there's a very important paper, for us, very important paper of Stolz in 1991, where he also discussed this problem. Okay, maybe this is a little sloppy mathematical background. Why we are interested in, well, actually we are interested in changing the weight because the weight, sorry, we are interested in changing the weight because maybe you know, you see Bernd and me, we come a little bit with a grind space background, and there it is very popular to consider indefinite weights. For example, there are some partial differential equations I don't want to discuss which lead to indefinite weights, and then from this point of view, it is natural for us to play with the weight, yeah? And also to make perturbations theory with different weights. Okay, I don't go into this detail. I don't go into grind spaces and so on. This is just the origin why we started looking at this problem. Okay, so let me recall some facts on on periodic Sturm-Liouville operators. So, as I said, I will start with the unperturbed operator and review some classic results, let's say, no? And then comes the perturbation. Okay, this is a repetition of our assumptions. Again, the weight and the P0 are always positive and periodic and locally integrable. And this is our standing assumptions. And then what one can do is the following. Well, as usual in Sturm-Liouville, right? We associate a so-called maximal operator to this kind of equation. This is A0, and here we take the maximal, so-called maximal operator. I don't define it in detail. It is the one with the largest domain of definition. Yeah? So the functions, so all functions from L2 which are absolutely continuous. Then you can make the first prime, and where after multiplication with P0 it is again absolutely continuous. So you can do the second prime, and then you say that the expression has to be in the correct L2 space. No? So this is, sloppy speaking, the maximal domain. Okay, and and then it happens due to the periodicity of our coefficients that the maximal operator is immediately self-adjoint. Yeah? So there is no need of extension theory, let's say, no need for limit, point limit, no need for boundary conditions which lead to self-adjoint extension, because our object is already self-adjoint. So from this point of view, everything is very easy. And it is self-adjoint in the weighted L2 space as usual. I said it before. So you take the L2 space and with a weight which you put into your L2 inner product. You multiply with a weight as usual. Okay, and then what do we have else? Or everything is due to the periodicity of our coefficients. So it is the spectrum is semi-bounded from below. It is, I will explain it later, but probably everyone knows. It is absolutely continuous. It's purely absolutely continuous and consists of finitely or infinitely many spectral bands, which is quite funny. So the spectrum is has a very nice structure. So I try to make here some kind of a picture, and well, you see these are the spectral bands. Could be, as I said before, could be finitely or infinitely many. Yeah? Okay, so. And how, well, I don't want to go too much into detail here. It's all a little bit, this is Floquet theory, right? So how to determine the endpoints? Well, I start counting the bands, and then the endpoints are given by the case eigenvalue of the corresponding regular Sturm Liouville, where we consider the expression over its period. The omega stands here for the period of our functions. Yeah, and you take specific boundary conditions here. So you have a regular Sturm Liouville problem, and then you take, in one case you take periodic boundary conditions, and in the other case you take semi-periodic boundary conditions. You compute the eigenvalues, and they give you the endpoints of the corresponding bands. I won't use it. It's just it's just a little bit to recall all the nice properties of periodic Sturm Liouville operators. And one more thing, because this I'm going to use a little bit all this theory. Well, you exploit these periodic properties a lot, and the theory somehow works, somehow sloppy speaking, that you start to prove properties of the eigenfunctions, corresponding to not eigenvalues, corresponding to solutions of the corresponding equation, and then you can show various properties of the solution of the solution of this equation. So let's say eigenvalue. I mean, we don't have eigenvalues, so but nevertheless you can consider this equations, and you consider this equation, and you prove properties of the solution. Of course, you always have two solutions of this equation. They are not, well, they are not then in the domain of our operator, but nevertheless you can study their properties. And well, and then a careful analysis of everything reveals the following: that if I consider, again, I consider this equation, I have two solutions, and it happens that they are bounded when I take lambda from the red area, from the spectral bands. And one has to be a little bit, I don't want to discuss this, one has to be a little bit careful with the endpoints of the spectral bands. The behavior is a little bit more difficult. Yeah, that's why I just wrote interior, to make it simple. Yeah, I don't discuss the endpoints. You can do, but not here. And I'm in the black area, which means not in the red. When I'm in the black area, when lambda is from my black area, always one solution is unbounded. Okay. Good, good, good. So this is what I wanted to recall, and especially these fact here on the solution. It shows also a little bit that you have good control on the solutions, and with a good control on the solutions, you can also later then prove something for the solutions of the perturbed problem, and then finally you can get also some assertions on the spectrum. Okay. Fine. Let me come to, that's why I put this here. Yeah, I will use this in a second because I want to show now the ponytail conjecture. It's quick, but it is somehow funny, let's say. Yeah. And we will use Hill equation here. I don't go into details. I make it very roughly, but the story is nice. So let's assume we are a running person and we have a ponytail. And sometimes, you know, it happens, it's a ponytail. Of course, the ponytail goes with the head up and down, yeah? Because it's fixed to the head. That's clear. And but sometimes it starts to swing to the side, lateral. Yeah? There's some lateral motion. And the question is somehow why it happens, when it happens. And this was, I think, really some kind of an open problem, let's say, to find a good model to describe it. Yeah? Well, you see, we have to read it clockwise, let's say, I think so at least. Well, this is clear, right? Jogger's head moves up and down, and the vertical motion is sometimes very unstable to lateral perturbations, and it is an example of parametric excitation. Maybe this one is not so important for us. And I take the next slide in order to explain it a little bit more in detail. This is the idea. Well, this is obviously the idea of these guys here, yeah, who got the Nobel Prize. Yeah? Okay, and I think this Keller guy, he is known for, he is very good in parametric excitation. They are physicists. Yeah? Okay, I won't go. I will not explain everything. So what they did? Well, they say, okay, ponytail is a swinging pendulum. Yeah? And swinging pendulum, well, probably there are many ways to do it. First of all, if you take pendulum equation, it is a nonlinear equation. Well, first thing you do is to linearize. So you write it, you take the linearized pendulum equation. And this is here a little bit, I put it here, maybe I can go one more. You see, here we have F2 prime, right? Here is F. Here is this G is the constant of gravitation. Yeah? L is a ponytail length, and A is some amplitude. Yeah, you can forget. And omega is sorry, this is wrong here. Omega is frequency of the runner. Sorry, this is okay. Yeah, here's some frequency, and it should be not. Yeah, it is a frequency of the runner. Sorry, no, I was too, but it's not so important. And now you can really plug in some numbers. Let's say, yeah, of course, gravitation on Earth, you know, length of ponytail, you know, and omega will change. Yeah, omega depends on the runner's speed, let's say, or how many steps he is making each second or each minute. Yeah, because this changes the gravitation. Yeah? And well, A for a while we can maybe forget. Yeah? So it says this is big capital L. Its natural frequency is 1.4 cycles per second. No? And then well, maybe I should explain. And this equation above. Look here. This is our this is our potential, right? And of course it is periodic, and we have no weight and nothing in front of f prime, yeah? Or only one. So this is Hill equation, as I said it here. This is Hill equation, and well, we could rewrite it as an eigenvalue problem, yeah, by putting this on the other side, and then we change omega. We change omega. This will change our Hill operator, and the spectral bands will move somewhere. I don't know. Yeah? And now, now the following question is, well, and then we take a solution of this equation, and depending whether now the eigenvalue problem is now in the red area or in the black, gives us stable and unstable solutions. Yeah, this is what, yeah. So if you do the computation, I won't do this, yeah, then it turns out that if I have this ratio between the natural frequency of the runner and the natural frequency of the pendulum of the ponytail, then I get a solution of the Hill equation from the red area. Sorry, from the black area, from the black area. So this is the idea of Keller somehow, to model it with Hill equation and to do it in such a way that suddenly for some lambda I hit the black area. Yeah, I hit this one, and then I get an unstable. I get the unstable, let's say, unbounded solution or unstable solution, and this is. Yeah, this makes everything because unstable means it grows exponentially, and then from a physicist's point of view, it is unstable, yeah, because things become very big and chaotic, and yeah. Therefore, when I have a tiny sideways motion, it will be amplified exponentially. I mean, you see, this is a big mixture between modeling and equation, yeah, right? So, but this is how physics work. So, it's funny that, well, let's say the rather simple Hill equation leads to a solution of this problem. And the funny thing is that really the numbers are correct, let's say. So, so runners which are really running quite fast, they reach 140 to 160 steps per minute. Yeah? So it looks quite reasonable. Okay. So now let's say this is somehow, I didn't put some new title in here. Now comes my second part of the talk. Yeah. So I will discuss perturbations. So up to now we discussed properties of periodic Sturm-Liouville operators, and now I discuss what happens after perturbation. So I thought maybe, oh sorry. I thought maybe why not to repeat all the used notions. So first one is a well-known resolvent set. So this is a set of all complex numbers such that A minus lambda has a bounded everywhere defined inverse. Spectrum is a complement. Then we have a point spectrum as usual. A minus lambda is not inactive. We can also speak about isolated eigenvalues with finite dimensional kernels. And these two notions, I just wanted to repeat them. Yeah. So one way to define essential spectrum is to say it's a complement of the Fredholm domain, or the other one is to remove all isolated eigenvalues with finite dimensional kernel. Please, I do these notions. All my things are self-adjoint, so I do it only for self-adjoint operators. So this notion of essential spectrum is very simple, and we can speak about the absolutely continuous spectrum. What is it? While you take the spectral function of the self-adjoint operator, you put it you put it, you consider this function here, which produces a measure. And if this measure is absolutely continuous with respect to the Lebesgue measure, then this X is a member of this space HAC, and this is used to produce the spectrum. No? Okay, just a repetition of all objects which appear. So again, I start with my unperturbed, periodic Sturm-Liouville operator as before. We discussed many properties of this guy, and well, then I perturb it more or less. Well, it looks the same, but it is not the same. Of course, the coefficients are different, and maybe I should stress it. It's we no longer assume periodicity of the coefficients. So everything else is assumed, but it can be that the perturbed guy is no longer periodic. No? Or normally it is no longer periodic. Okay, so of course we need also some more assumptions. There must be some relation between Q0, Q1, P0, P1, R0, R1. Otherwise, it would be totally arbitrary. Clearly, yeah. So, and this is what we assume. What is it? It is written in a little bit condensed form. So it is the following. You see, this object in the big brackets is integrable, is summable, which means that the three differences are summable. Yeah? So R1 is different from R0 in some L1 sense, and so on and so on. Yeah? 1 over P1 minus 1 over P0 is an L1, and so forth. So this is the first. I will show you 3 results, and while this is they are related to each other because the assumptions looks a little bit similar. So that's why we have here a k equals 0. Where is the k? K is absent. K is here. No? So because I have 2 other results I want to present, I want to write it in a uniform way. Yeah? So it is the same to plug in here. So we still are in the case k equals to 0. Because t to the power 0 is 1, so it doesn't change anything. Yeah? It's convenient to write it like this, because our second type of results is the following. Yeah? There we have this t. Yeah? So it's some kind of first momentum, if you want. Yeah? Multiplied with these 3 functions. And then we also have for k2, well, this is some kind of second momentum. So these are the 3 assumptions we will have. And then we will discuss the spectrum of the perturbed operator. No? Okay, let's do this. So let's start with k equals 0. So you see, I repeat here our assumption. This is our assumption. So the differences of the corresponding coefficients are summable. No? And then now comes the result. So yeah, I do it in pictures, and also I will say some words. So you remember that the spectrum of this is here A0 is our unperturbed operator, right? And then we have some A1. This is our perturbed operator, yeah, corresponding to the corresponding differential expression. Both operators are self-adjoint. So you see what can happen. Well, I summarize it here down below. So the spectrum of the perturbed operator has the following properties. First of all, you see it a little bit in the picture. The essential spectra remains the same, which is good, of course. Then, as I said, always the endpoints of the spectral bands are a little bit nasty. No? So what we have, the purely absolutely continuous spectrum of A1 is the interior of the essential spectrum of A0. So this is this is what can happen. Yeah? So it means that, for example, there could be an eigenvalue of A1. Yeah? So now, so the blue ones, the first two items are somehow good. Yeah? Now comes the bad or the unsatisfactory results. There can be infinitely many eigenvalues in the gap. And as I said before, the band edges can be also eigenvalues. No? Okay, and now we continue. So we add now, we increase our assumptions. We add now more stronger assumptions, which is of course setting k equals to 1. Yeah? So this is our next result. If k equals 1, which is stronger than k equals 0, yeah? Because all these objects are locally integrable, so okay, it's clear. So what happens? Well, this is a spectrum again of the unperturbed operator. This is the perturbed guy. Well, I put it now all in one. I mean, the first two blue points we still have from the first. Yeah. So again, k equals 1 is stronger than k equals 0. So the first two items from the last slide we have nevertheless for free. So I just repeated shortly, the essential spectrum is the same. The purely absolutely continuous spectrum is again the interior of the essential spectrum. And now finitely many eigenvalue. Now we have, now what happens is we have only finitely many eigenvalues in the gap. So this I call it Rofe-Beketov type result because he was the first one coming up with this point. Yeah? But in his paper, the weight was the same, and the coefficient p or p0 in front of the f prime was also the same. Yeah? He'd only played with the potential. But okay, he became quite. I would say he became quite famous for this. And what we have here, okay, still the band edges can be eigenvalues. No? So this is unsatisfactory. And well, now you can imagine what happens. We increase our assumptions even further. K equals to 2 again. Yeah, we have now t squared. Again, we get this is stronger than k equals 1. So we get everything from the last slide. So yeah, also here are the pictures. So we get everything from the last slide, but now we get here that the band edges are no eigenvalues anymore. I also put it here in the item number 4 because these two are connected. So it is essentially the spectrum of the perturbed object is essentially like the spectrum of the unperturbed object. Only it may only happen that finitely many eigenvalues. This we still have, so it can happen that finitely many eigenvalues are in a gap. Yeah, I think that's all. I think I can stop here. Thank you for your attention.
I have a question on the previous slide. So the special case can be A1 equals A0? Exactly the same?
I don't, of course it could be the same. I don't understand.
So I don't understand, absolutely continuous spectrum of A1 is interior of essential spectrum.
Yeah, I have to admit, this is a typo.
That's a typo.
Yeah. You have to well, let me. Yeah, 1 second. A little bit. You still can see my slides.
Yes.
Yeah. Here it was here. Yeah. It must be. This is just an inclusion. Sorry. Yeah. You are totally right. It could be the endpoints could be also part of the absolutely continuous spectrum. As you said, you just take the same operator. Then
Right.
yeah. Sorry, here's only some inclusion. Yeah.
Okay. So that's so essential spectrum changes to absolute continuous spectrum is rather drastic.
Sorry, the acoustic is very, very limited.
The essential spectrum is not stable.
No, it is. No, it is stable. You see, the essential spectrum is always the same. But then you can pose the question: is it absolutely continuous spectrum?
Oh, I see.
Yeah.
Okay. That makes more sense. Any other questions from?
I have a question, but it may not be easy. Is there some physics intuition that helps us understand the difference between the three cases, k equals 0 and 1 and 2?
Yeah, that's a good question. Yeah, no, no, I have. Well, I'm not so close to physics. That's why probably it would be interesting to know. Yeah, of course, it would be. Everything in this periodic Sturm Liouville has very, very nice physical interpretation. So it would be nice to have this also. But I don't know. Sorry.
It sounds like something Joe Keller would. Okay, thank you anyway.
Okay, thank you.